receive Eleonore Faber, who will give us the second of her talks on matrix factorizations. Please, Eleonore.
Okay, thank you, Hipólito. I can hear myself. So, oh, okay, now it seems. Oh, it's better. So I hope everybody can still hear me, and I can not hear me. So I just wanted to recall what we did yesterday. So the definition of matrix factorization is on this board. And as always, S is either a graded polynomial ring or a complete regular local ring. You can do a little bit better than complete regular local. It should be Henselian, but you want to have some kind of Kroll-Schmidt property. And then, yeah, matrix factorization is always given by a pair of matrices. And so a matrix factorization of F, so you have to fix some non-zero divisor F, and then you have to satisfy these identities. So A times B is B times A is F times the identity matrix. And then, so yesterday I did define this category as a category of all matrix factorizations. What I did not define is the category of reduced matrix factorizations, which is you mod out by the two trivial matrix factorizations that will play a role more prominently tomorrow. And this one here is just you take all matrix factorizations and mod out by the 1 and F, which doesn't really give you a maximal Cohen-Macaulay module. And then the last theorem I did yesterday was Eisenbud's theorem about the two periodic resolutions. And then there's another theorem of Eisenbud, which is like the equivalence of categories of maximal Cohen-Macaulay modules in matrix factorizations. And so we can also recall how the functors go. So this is all in Eisenbud's paper from 1980, and in particular in section number 6. So we have R is, as always, S mod F, so the hypersurface, and we mod out by the polynomial or like this element F in S. And then we have an equivalence of categories, namely the category of matrix factorizations, where we just mod out by this one. This is equivalent to the category of all maximal Cohen-Macaulay modules over R. And so we did that yesterday. So if we take a matrix factorization AB, then what's the Cohen-Macaulay module? We just send this to the co-kernel of A. And then the other way around, if we have a maximal Cohen-Macaulay module, then, well, we take the, so it's like of projective dimension 1 over S, then we construct the maps A and B. So we get like this from computing a free S resolution of M, and then we get the matrices A and B. And then, moreover, this restricts to an equivalence on the reduced categories, namely, we get an induced equivalence. The reduced matrix factorizations of F are equivalent to the stable category of maximal Cohen-Macaulay modules over R. So this is just, we take all MCM, R, and then everything that factors through projectives. And so this is just direct sums of R in this case. Okay, so, and of course you have to somehow prove something that these are like really inverse functors, but yeah, I'm not doing this. So a nice account of all of this is actually in Yoshino's book, and he proves all equivalences and all the construction I did yesterday in detail. But I wanted to do one corollary of this theorem, because well, we have a matrix factorization. These are two matrices, and we are only getting here like co-kernel of A. So you might wonder, what about B? And well, is what you probably expect. So if we have M and MCM R, and if we assume that M is indecomposable and also non-free, then, and so M is the co-kernel of the matrix A, and so where AB is the matrix factorization of F, then, well, I can compute the syzygy of M. So I denote this by omega M. So then omega M is also indecomposable and non-free. And well, you can like guess what it is. It is precisely the co-kernel of B. So this is how we get like those two modules. And then one more thing that I didn't came to mention yesterday, but I talked with some people about it, so probably you're interested in that, because this is some kind of more representation theoretic way to see matrix factorizations. Namely, alternatively, you can describe matrix factorizations as quiver representations. So I'm not doing this in detail. This is actually, I sent Hippolyto the notes from yesterday, and there it's explained in more detail. But essentially what you're doing is you're looking at the quiver, at the path algebra S of this quiver. So instead of over a field K, you do this over the ring S with two vertices, E plus and E minus, and we have two maps, V and U, and you have a bunch of relations, and so the relation here we have is UV minus F times E plus, and VU minus F times E minus, and then yeah, you want that these are the idempotent, so you need those relations as well. But so you can now look at modules over this path algebra here, and then yeah, then you can also define what are maximal Cohen-Macaulay modules over this path algebra. These are precisely modules over B that are maximal Cohen-Macaulay SS modules. But what you can show is that actually matrix factorizations correspond to where you put here projective modules. And in particular, you can get them at the matrix factories, so the maximal Cohen-Macaulay modules over R from a recollement, namely, if you go from mod B to mod B and you mod out by BE minus B, and you can see that this is just S mod F. So here I'll just draw the one functor that is giving us the equivalence. It's just tensoring by E mod B E minus B. Then this restricts to an equivalence on the level of maximal Cohen-Macaulay modules. And what you can show is that the maximal Cohen-Macaulay modules of B, which are just the matrix factorizations of F over S, and yes, for the reduced matrix factorizations here, and I have to mod out by B E minus, oops, sorry, by the idempotent B E minus B, and this is nothing else but the maximal stable category of maximal Cohen-Macaulay modules over S mod F. So this is like another way to see that. And yeah, an account of this is in this paper. Buchholz and Ingels. Somewhere hidden because we're not really, we're looking at reflection groups, but it's in section 4.1 that is explained in detail. Okay, so this was just a remark. And so now I come what is actually was supposed to be the second lecture. And well, okay, 10 minutes are gone, but it's not too bad. So today, the main topic is to discuss a bit about how to find matrix factorizations, and then, well, how many matrix factorization / Cohen-Macaulay modules are there, which leads us to this finite Cohen-Macaulay or Cohen-Macaulay representation type. And so this Cohen-Macaulay type, and then the main tool to deal with the the question of finite Cohen-Macaulay type over hypersurfaces is the so-called Knurrer periodicity, which will tell us how to somehow jump dimensions, and which is a nice application of matrix factorizations. So, as I said, two questions. So question one is, how do we get matrix factorization? How to construct matrix factorizations? So in particular, I was asked yesterday after the talk, can we always find a matrix factorization? And well, yes, we can. So there's a nice construction by Eisenbud. And the question two is, how many non-equivalent, of course, matrix factorizations are there? Okay, and I should say, so all of this, so also if you want some references for the topics I discussed so far, more or less everything is in the books of Yoshino. So it's called Cohen-Macaulay modules over Cohen-Macaulay rings. And then there's also a book by Leuschke and Wiegand, which deals with the same topic. It's called Cohen-Macaulay Representation Theory. And then, yeah, also Knurrer periodicity will be there, but most of this question two part here is from the papers of Knurrer and Buchholz, Royal, and Schreier. Okay. So, good. So here we are. So first, well, how can we construct matrix factorizations? So, well, if I give you a random polynomial, how can we do that? And so this is Eisenbud's construction. And I wanted to recall this because this is somehow, whenever people construct matrix factorizations, especially like in the physics context, this is somehow the method to do that. And so, well, so we start again with the usual. So we have our S is either a graded polynomial ring or complete local. And for this, we have to assume that the S, as always, and well, F is a non-zero divisor, but here we need that f is actually also in some sense singular. So it's in the square of the maximal ideal. So if S is complete local, then we have a maximal ideal in the polynomial ring. You just assume it in the irrelevant maximal ideal squared. And so if we have something that is an m squared, then we can always write it as a sum of products, namely, so we can write, so this is in no way unique, but we can write it as a sum from I to R of xi and yi for some elements xi and yi in M. So yeah, important, this is not unique, so you can do many different of these sum decomposition. And then we can construct a matrix factorization on the exterior algebra of S to the power R. And so this works as follows. So we define some linear maps on this exterior algebra. As R. So, okay, I guess I can continue here. Sorry? Oh, yes, sure. Get some more exercise. Maybe I'll put that up and the other one down. It's readable. Okay. So how do we get a map on this exterior algebra? So we define it on a basis. So we take some basis E1 up to ER of SR. And then, well, if we are in the ELF piece, then we define two maps, a differential of degree -1 and one of degree +1. Namely, the minus differential is we take the element EI1, which EIL, so we're in the ELF exterior power. And this is just the usual, I want to say. So we start from j is 1 to L, and we go from j -1, and then we take here x ij, ei1, we leave out the jth element, ij here, and eil. So that lowers the degree by 1, so we just leave out the jth element here. And so the important thing is we multiply with the x's. So if we go down, means multiplication with x. And going up is the delta plus. So this is easier to write down at least. So we take a homogeneous element of whichever degree we are, and then we just wedge it with the sum over R, yj, bj, with w. So here you see the yj up here. And so this will increase the degree by 1. And so now, well, a little exercise for everybody. We can show that indeed what I'm saying is true, namely that delta plus and delta minus are differentials on the exterior algebra SR. So they square to 0. And then also the degrees. So the degrees are +1 and -1. So this is more or less clear. And then the second part of the exercise is what's then giving us the matrix factorization, namely we set delta to be the sum of delta plus and delta minus, and then, well, if we compute delta square, so, well, you might think this is 0, but indeed it's not. It is precisely f times the identity SR. So you see that this will give us the matrix factorization. So indeed here, this is actually not, so if you really do the calculation, what you show is that this delta square is delta plus, delta minus plus, delta minus, delta plus, and then apply this to a basis element and see what happens. And well, you see that f is just the sum of this xi and yj, and you get what you want. So the result of this is that delta comma delta gives us a matrix factorization of f. And well, and then so this can be divided in delta plus and delta minus, and you can construct this for whichever f you want. And so you can play around with this, like trying to use different sum decompositions of f, and so maybe you get equivalent matrix factorization, sometimes you don't. I actually worked out the example of r equals 2 in detail, and you can probably get this in my notes, but you can also try to work it out yourself. Okay, and if we want to know more about this, so this is all in Eisenbud's paper, but it was then generalized to complete intersections, and there is a paper by Abramov and Buchweitz, or this is explained more generally. Okay, so I'm going to write down the reference. So Abramov and Buchweitz, 2000, and so they did complete intersections. Okay, so far so good. So this was well, at least one answer to question number 2, number 1. And so now question number 2, which is interesting from a representation theoretic point of view. Well, we come to that now. So this is chapter 2 for today, namely finite Cohen-Macaulay type. And so the goal is, well, let's see how far I get. But the goal is to show you, at least for hypersurfaces, these finite Cohen-Macaulay type hypersurfaces are completely classified, and I'll show you how this can be proved. Okay, so first of all, I should define what I mean with finite Cohen-Macaulay type. So if we have any commutative, or like any ring where we have maximal Cohen-Macaulay modules, so that R EA. So this is not relevant, but have so far only defined maximal Cohen-Macaulay modulus over commutative ring. So let R be a commutative ring. And then R is called of, well, R is not called, R is of finite MCM type or Cohen-Macaulay type, or sometimes this is also called representation type. Well, if we only have finitely many non-isomorphic maximal Cohen-Macaulay modules. So it has only finitely many non-isomorphic maximal Cohen-Macaulay modules. And well, for hypersurfaces, so we have seen maximal Cohen-Macaulay modules are the same as matrix factorization. So you are asking, you have finitely many non-equivalent matrix factorizations. And well, you can phrase this differently in saying that MCMR admits a generator. So meaning that MCMR is additive category of some module M in R. Okay, so this is the definition. Well, so you might ask, what are rings of finite Cohen-Macaulay type, and particularly hypersurface rings? And so, well, I think I gave you one yesterday, namely this this cusp, where I said, oh, well, we only have 3 different matrix factorizations. So that is an example. And so the example is for hypersurfaces. So here there is finite MCM type is classified, namely, so now it becomes a bit complicated because somehow depends on the characteristic of the field. So if so if the characteristic, so in general, these are just the simple hypersurface singularities. And so this is so simple. I'm not defining this in its way, but this is sometimes called rational double points. And so if the characteristic is greater or equal to 7, then these are just really the ADE hypersurfaces. So maybe I should make it clear what my setting is. So hypersurfaces, I have S mod F, and now here I assume that S is really the power series ring in n variables. And so if K is algebraically closed, and the characteristic of K is greater or equal to 7, then these simple hypersurface singularities are the A, the E hypersurfaces. So this means that F is of the form x1 squared. Oh, yeah, I did something not very clever. Maybe I'll just add two variables. So we have like sum of squares, which we can then neglect, and so y squared plus z to the n plus 1. So this is type an. Then type dn is, again, we have here the sums of squared, and here we have y times z times y to the n minus 1. I hope this is correct. Please correct me if it's not. Then we have e6, that is y cubed plus z4. And here we have y z plus, oh god, I didn't draw this on, I didn't write it out, and now I'm confused. But what do we get here? Wait, I think we have yz squared here, and here we should have okay, whatever the right term is here, I'm sorry. And for E8, at least I remember that one, that is E8. So of this type, and if the characteristic is 2, 3, or 5, then you have a little different list, but you still have this kind of similar classification. And so this is the result. So this is hypersurfaces, and this is what I'll probably only prove tomorrow, that this is actually true. But what else is known? So this is example number 1. So if you go away from hypersurfaces, the answer becomes much less easy. Namely, one thing that is still known, namely dimension 1 and 2. So in dimension 2, we have the following nice result. So if R is a Cohen-Macaulay ring, and also R is normal, which means that it has only isolated singularities, or it's R1 and S2. So then R is a finite MCM type if and only if R is isomorphic to a invariant ring under a finite group. So G is some finite group in GL 2K. And so, yeah, for this result, whoops, and small k. So for this result, this is due to Auslander. And there is also a geometric proof of one direction by Hainaut. So, well, for this, you also need that. So you definitely need that the characteristic of K is 0 for this proof. because we need some argument, some topological argument of Mumford to prove this direction. And the other direction, finite Cohen-Macaulay type, implies this direction. So if you have invariant ring under a finite group, then this has finite Cohen-Macaulay type. This is true whenever the characteristic of the field does not divide the order of the group, but this direction is only true in characteristic 0. Okay, then, so this is dimension 2. Well, in higher dimension, it's more or less open. So if R is Cohen-Macaulay ring, so just any Cohen-Macaulay ring, then the problem is open, and the dimension of R is greater or equal to 3. So the only thing is there are some examples known, and there are conjectures that these examples are the only ones. But it's not really proven. And so one thing that is known is the theorem of Auslander that says that finite Cohen-Macaulay type implies isolated singularity. So this already narrows down the candidates for maximal Cohen-Macaulay type, but you still have like a lot of finite Cohen-Macaulay type rings that are Cohen-Macaulay and have isolated singularities. Well, you can also show that if we have, for example, if you have a Gorenstein ring of finite Cohen-Macaulay type, it has to be actually a hypersurface ring. So, and we know those. But yeah, if you have any idea about this, then well, this would be something new. Then, yes. Yes. So if you have plus y, yeah, that is finite Cohen-Macaulay type. It's okay. So this is so this is if here in this example, like you don't have any x's. So basically you just yeah. Oh yeah. Oh, sorry. Yes. Yes. That. Thank you. Okay. Oh yes. Sorry. This is. Yeah. So this is. Yeah. This is some number of. Thank you very much. Yeah. Yeah. I should really prepare everything that I'm saying, but so yes, this is just some number of variables, and L might be 0, and the important part is the last one here, and of course these are the finite Cohen-Macaulay type curves. Okay, so this is all about Cohen-Macaulay type, and yeah, you can also like define what is then tame Cohen-Macaulay type and wild Cohen-Macaulay type in accordance to the representation type, and yeah, much less about this is also known. Okay, so well then let's come back. At least starting with like how to show that these are the only hypersurfaces of finite Cohen-Macaulay type. So the idea essentially is you first show that these like when L is equal to 0, so the curves are finite Cohen-Macaulay type, and then you can just add squares. And somehow adding squares doesn't change the Cohen-Macaulay type. And you can like describe how the maximal Cohen-Macaulay modules change under adding squares. And this is then what Knorr periodicity tells us. Okay, so let's do this. So now to prove the example, what is it, 1? So this is section 3. Periodicity. Okay, so we are back to hypersurfaces now, and so first we're looking at like what happens if we add a square, and so for this we define the double branch cover. So if we have R is again S mod F, then the double branch cover of R is R sharp. So this is we add a variable. So now S, yeah, think of S as the thing with the X variable. So we add the variable Z. And so this is just, we add one variable and then we mod out by F plus Z squared. So geometrically, you see that the spectrum of this is like ramified over this variety defined by F. Yeah, and so in order to like make all of this work, we also assume that K, I have always little k, K is algebraically closed, and the characteristic of K is not equal to 2. So why one comment about why do we need algebraically closed, why we need characteristic not equal to 2 will become more apparent later. But so in order that this is really, this double branch cover is well defined, this is why we need the algebraically closed part. Because, for example, if we would take K to be the real numbers, then of course we can look at the ring R that is R X mod X squared, and hope you agree that this is the same as the ring X mod minus X squared. But then if we add the Z, we will at the Z square, this is a problem, because if we add it to this here, that is R sharp is then R X Z mod Z squared plus X squared, which is irreducible over R. So, well, it's irreducible. Or here we would get R X Z and Z squared minus X squared, which is not irreducible. So in order that we don't get into these problems, we assume that K is algebraically closed. So then this double branch cover is uniquely defined. Oh, 2 minutes. Okay. Well, well, at least I defined the double branch cover. And so now I can at least start with comparing the maximal Cohen-Macaulay modules of R and of R sharp. And then eventually we will also look at the double branch cover, which is R sharp, or you can, if you like musical notation, you can do like the double cross. Okay, so first let's do this one. Okay, I have 2 minutes. I can probably define how to like the functor from here to here. We have always a surjection from the R sharp to R. So well, what are we doing? We just mod out by Z, so we kill the Z. I'll just write here mod out by Z. And also, if you look at R sharp as an R module, as an S module, then here it is. So R sharp can be written as S plus S Z as S module. And so this will be used. And so now if we have a maximal Cohen-Macaulay module over R, how do we get a maximal Cohen-Macaulay module over R sharp? So R has like one dimension less than R sharp. So this maximal Cohen-Macaulay module is not maximal Cohen-Macaulay over R sharp because the depth is too small. But well, what we can do is like we can take a resolution and take the syzygy, the depth is going up, and we have a maximal Cohen-Macaulay module. And so this is the definition of so if you have M in well, we can define this for any module in mod R, then we define M sharp. We just take the syzygy of M. So M is an R sharp module, but then we take the syzygy over R sharp of M. And this is, of course, in mod sharp. And well, if this is in MCM, then this guy here is in up. And then how to get from R sharp down, this is then flattening. So if we take a module N in mod R sharp, then we define a module over R and flat by modding out by Z. And so this gives us a module over R. And indeed, if this is maximal Cohen-Macaulay, then this here will also be maximal Cohen-Macaulay. And so I think, yeah, just one more thing I want to say. If you want to play around with this, then the first module you want to consider is like R itself and R sharp itself. So you can actually show the remark or an exercise that if you take R and you sharpen it, then this is precisely R sharp. And if you take R sharp and you flatten it, then this is R. So wait, sorry, this way. Yeah. Okay, so that's it, and to be continued.
Thank you very much, Eleonore, for this talk.
Can you try now?
Yeah. Hello. Yeah.
Wait.
Okay.
What? Oh, good question. Good question.
Can you hear us, Polito?
Irreducible representation
Hipólito?
times
Yeah.
many.
Yeah.
So, oops.
Sorry, could you repeat the question that you were asking? Yeah.
Okay, I can, a little echo. Okay, I guess it's okay. So Ralph asked, like, how many are there? So the answer to this question is, well, the answer is, so yeah, so I still have this result here. So in particular here, so so let's look in dimension 2. So in dimension 2, you have the result R is a finite Cohen-Macaulay type if and only if it's the invariant ring of a group. And in particular, if this G is in SL2, then it will give you the Kleinian surface singularities. And then it is like the Mackay correspondence then tells you that the maximal Cohen-Macaulay modules over this invariant ring are in one-to-one correspondence with the irreducible representations. So you get irreducible representations, many of these maximal Cohen-Macaulay modules. And so now this is dimension 2. Then in dimension 1, you have these curves. So you can see these curves as discriminants of the corresponding reflection group. So here you have like, so for the surfaces, you have G in SL2C, and then this sits in index, sits as a subgroup of index 2 in a reflection group. And so these curves here, so in 2 variables, can be seen as discriminants of this reflection group. And then the maximal Cohen-Macaulay modules are in one-to-one correspondence with the non-trivial irreducible representations of this reflection group. And so that's dimension 1 and 2. And so now it's like a big spoiler is that if you go up in dimension, it's always the same number, because what we will then see is that MC, so where is this double branch cover? So we will see that this here is actually the same. And we have, if we take the stable category, then this will just be the same. And so you will, in any dimension, you will just get the irreducible representations of this like group G or G prime. And yeah, and you can also then you can also look at the Aus-Underreiten quivers, and yeah, they're like in any dimension they are the same, but the only thing is, yeah, you have to make be a bit careful what happens with the trivial representation. That a number of arrows always, like if you go up 2 dimensions, it always doubles. Yeah, that's the.
Okay, thank you very much for this beautiful talk. I think if there's any and ask Eleonore if you're in person there. Maybe we can take a 3-4 minute break until the next talk. Let's thank Eleonore again. Thank you very much.
Thank you.